Now we've got another section to do in the work energy power. It's quite a long section. I'm going to look at vertical motion type problems. The same, and we're going to look at the work energy theorem. Now, let's just imagine what happens when we throw an object up into the sky, the vertical projectile. If you remember previously what we said that we've got two sides to this motion, right? Let me just check. Yep, there we go. We said we throw something up with a V initial. Remember, we said we do this, okay, and we split it into the up and the down side of the motion. Now, we started off with an initial velocity. If we don't, it's not going to go anywhere. Bearing in mind, we could also be doing this, couldn't we? Right? We could be throwing something down with an initial velocity. That just means that we're going to add the acceleration essentially onto it, aren't we? But let's look at it from an energy point of view. This, at this point, has got an EK, hasn't it? So when we throw it up, here we go, right? This is going to go up like that. So I launch it here with a kinetic energy. Let's take the green one for a change. So we launch it with a kinetic energy. We have EK here, and at this point my EP is 0. Now we said at the top, remember we said V final equals 0, V initial equals 0 over there. This is how we used to do it. Now we say, but hang on, at the top my EK is equal to 0 and my EP is equal to mgh. Correct? This is an interesting situation because it means we can use energy to solve these problems as well. That's a cool one because it's actually, if you look at it, independent of the mass. I'll show you why in a second. Let's just have a look. At the top, right, at the final position, at the initial position, we've said that the energy is 0, or the potential energy at the bottom 0. So what actually happened? What happened was that the kinetic energy was transformed to potential energy. Remember, it's the same thing as previous where we had the pendulum. Remember, we had a pendulum, my apologies. We had a pendulum which went like this over there, and it swung down like this to somewhere like that. And we said here the EK was 0, the EP was equal to mgh, where that is h over there. And over here, EP equals 0, EK equals a half mv squared, right? So this is a similar type of process. Therefore, we can work out using energy principles exactly how high it's going to go. How do I say that? Well, the law of conservation of energy says that if there's no external forces, then the energy must remain constant. So the energy you start with must remain constant throughout the entire process. I hope you remember the roller coaster problems we did a while back. Remember we said that the energy I started with remains constant at any point. And what did we do? We said point A, we work out the energy there, and then we go to the other places and we work out our EP and our EK, and we put them equal to each other. Essentially, we say that the energy at A must be equal to the energy at point B, the energy at point C on a roller coaster. So we could have this kind of thing there. If that's A, that's B, and that's C, the total energy at both points must be the same by the law of conservation of energy. So what's the next step? The next step is then to say, in this case, the energy initial and the energy final must be the same. So what do? I said that therefore mgh, this is my E at the, let's say, final at the top, must be equal to a half mv squared. This is E initial. Well, straight away, I can divide through by m. So gh is equal to a half v squared. And essentially, that's the formula we're going to be using, right? Now, that's straightforward for the energy problems, for going upwards or even downwards, as we said before. But let's now have a look at the last section of this, okay? We're going to do some problems of these as well. Right. we're going to look at the work energy theorem now. And in the work energy theorem, what if there is an external force applying? We know that when this ball goes up, for example, it doesn't go as high as it should. Why? Because there's air resistance on it, okay? So we have to account for that. So what do we do? Well, let us consider an object, okay? An object over here. Let me just erase these dots. There's let's say a piece of ground over here, and there's an object coming in here, and we say Fg is equal to 9.8 m. mg, 9.8, right? I've just basically, without putting in a mass itself. This has got a V initial here. And let's say it slides some length with a V final over here. Now, let us say, here we go, I'll use my proverbial box again. So, this thing has got a velocity here, and when it comes to here, it's got a different velocity. Let us say it has slowed down. What slowed it down? Right? Friction, yes. And friction is a FF acting that way. And remember, FF is equal to mu times F normal. Just in case they give you a problem where they give you mu. Can you see the recipe's the same as all the previous we've been through? It ain't going to change, sadly. So we say, okay, cool. The next step is to say, we have got a block over here, all right? And over at this point, it's got an EK equal to a half mv initial squared. That's the kinetic energy. The EP over here is actually 0. And the EP over here is actually 0 as well. Why? Because we're taking the datum, that's a word. The datum is the reference point. Okay? We spoke about this with the roller coaster problems as well. So we're keeping it flat. Now our next situation is we're saying, right, this is going to stop or slow down. The friction is acting against it. The last part of this type of problem is we say, right, they give us a delta x in meters to say that it has slowed down. Now let's have a look at this work energy problem, shall we? Well, first of all, we said that we had an E initial and an E final, right? And we've always said the change in energy is going to be E final minus E initial. So now, in the previous examples, where there are no external forces, no resistance, no air resistance, no friction, we said we put final and initial equal to each other. What do we do now? Well, we've said that final and initial are not the same. The final might be less or more, it doesn't matter. But let us take the friction case where it slows down. We would then say that the change in energy is equal to minus some number, right? Because initial is higher than final, right? Just for argument's sake, say that my E final was 10 joules and my initial was 20 joules. Therefore, I've got a loss. This is a loss of energy, right? In other words, 10 joules, okay, is the final energy and the initial energy was 20. Could be 0 and 20. All I want you to see is we've lost energy, and I know I'm doing those quotation marks, which is a pain, isn't it? But anyway, what are we saying? We're saying that energy has gone. But energy doesn't go. It changes from one form to another form. The forms that it's going to use is it's going to change. It's going to go. Where does it go? It goes into friction. Let's go back. Come on. Just go back. It goes here, doesn't it? That energy that's gone is the frictional force times the distance, isn't it? The work done by frictional force, work done by friction, is equal to FF times delta x, right? That is where the energy went. It went into FF times delta x. In other words, let's just restate it. We can say that the work done must be equal to the change in energy. All right? Final minus initial, if you like. E final, that's not a nice one. E final minus E initial. So the work done is the force times the distance, right? So this is the energy lost, all right, due to friction. It's been changed to heat and sound, etc. And the other one is the change in the energy itself. I hope you can see that. It's not really that difficult a concept if you think about it, is it? All we're saying that the external forces have changed it. Let us take, okay, I've got here an example, all right? Well, let's just take something here. I've got an example here, right? We said that, remember, we said, let's say E initial was equal to 20 joules. And we said that E final was equal to 10 joules. Therefore, the force times the distance must be equal to E final, which is 10, minus 20, which is E initial, which is minus 10 joules. Let's just examine. This is negative, right? Why is it negative? We have lost energy. So you can see here that, let us say that the distance was 2 meters. Force times 2 must be equal to minus 10. Therefore, the force is minus 5 newtons. What does that minus mean? It means it's acting the opposite way to the velocity. That's all. Okay? That's all it means. And you'd expect that. If the energy is going down, you'd expect some force to be pulling it back, wouldn't you? Well, what happens if the energy goes up? You have added a force in to do so, right? Remember, if we go back to the previous, that was the change in kinetic energy. It's going both ways, isn't it? So the total energy in the system is going to be equal, with the exception of the fact that we could have added or removed some energy via adding in a force or adding in a force in the opposite direction. All right? Just let's have a look at an example, right? If we have, let us say we have an object which is thrown up, all right? Now, according to Newton's equation or the energy equation, let's just say it is thrown up with a V initial equal to 50 meters per second. Therefore, EK over here is a half times mv squared, correct? Could weigh 10 kilograms. Let's say it weighs 10 kilograms. But please note you don't need it. Okay, EK is 10, so that's going to be a half times 10 times 50 squared, right? Which is going to be 5 times 50 squared. 50x squared is equal to that. And times 10 minus 0 equals that. Divided by 2 is 12,500 joules, right? Now, let us work out how far will it go. So EP, this is initial, and E final is equal to a half times mv final squared, which is 0, plus mgh, right? That is 0 plus 10 times 9.8 times h. Therefore, is equal to 98h. Therefore, h is going to be equal to, because I'm going to say, let me do it fully. Okay. What would I say? I would say the two energies must be equal. 98h must be equal to 12 1.500. H is going to be equal to, divided by, is going to be equal to whatever, 127.55. Right? Now, what if we actually measured, all right? What if we measured actual height of 100 meters? What happened? The EP is equal to 10 times 9.8 times 100, which is going to be equal to, let's work it out, 10 times 9.8 times 100 is 9,800 joules. Therefore, let's have a look. What happened here? Okay, I'll just keep it. So we say, right, we have now, there's a discrepancy. Therefore, work done by an external force must be equal to delta E, which must be equal to E final minus E initial, which is final is 9,800 minus E initial, let me just go back, was going to be 12,500. Right? So therefore, you can see that minus 12,500 is equal to minus 2,700 joules. Okay? That is the energy that we have lost, is it not? Therefore, what is the air resistance? You can say that energy is F delta X. Therefore, that's F times 100 is equal to minus 2700. Okay, and therefore, the force is going to be equal to minus 2700 divided by 100, which is going to be minus 27 newtons. Minus means it's acting in the opposite direction to the movement. Right? Similarly, we can have an object. There's a couple of good ones. There's an object which is moving upwards and it hits something. Okay? It hits a branch, for example. All right? So let's just take this one here. What would we do? Let's say we project an object up. Okay? Like so. Okay? There she goes. And forget the down. Now, we've put it up with a velocity here. And at this point, okay, it transitions through branches that are out there. This is A, that's B. They might give us the delta X over here, or they might give us the time. What do? We say, right, what's the energy here? This is EK, isn't it, where we start. At this point here, when we've got to that height, I've got EP over here, right, which is equal to mgh at that point. And I've got an EK there. What happened between there and there? Let's put it in red. Okay? What happened between there and there? There was a force acting down of the branches. So we would say F delta X must be equal to E final minus E initial, which is the energy at B minus the energy at A. B, A. All right? If you've got that one in your books, have a look at it. Because that's all we're doing with it, isn't it? We're just saying, split it into sections and approach each section independently. Okay? That's the way to do these problems. Don't, and of course, draw it, right? That goes without saying. I think we've established that well enough now. What you're going to do is you're going to draw it and look at this data you're given section by section. So the first piece of data, you're given a ball or an object going upwards. All right, work out its energy, then work out the energy at the various other bits and pieces in the process of it going up. Okay, as I said, we're going to do a few more of these. Basically, they're all the same kind. You get an arrestor bed type problem, right? Let's just very quickly go through an arrestor bed. All right, what is an arrestor bed? Well, an arrestor bed are those things that if a truck gets out of control, you kind of want to stop it before it plows into something. So what it does is it runs into a long straight piece of road that's filled with sand or with gravel. So it sinks down to its axles and the friction stops the truck. You've just got the answer. There it is. So we say, right, here I have got my truck coming in. Okay, there it is. No, I'm not an artist. V initial. And over delta x, what happens? We wanted to get to V final of 0. So this has got an EK over here equal to a half mv initial squared. And the EK over here is 0. All the energy is gone. Where did it go? Okay, let's see. What stopped it? FF. Therefore, FF times delta x must be equal to E final minus E initial. That's all you have to do with the arrest to bed type problem. Okay. They will tell you, given this velocity to there, is the bed long enough? Calculate the theoretical distance needed and check it versus the bed. All right. If you go maybe I shouldn't go into that, but for those of you who go the other way, you're going to get a negative length, which means it has stopped already. Those of you who've done it that way, you'll know exactly what I'm talking about. But can you see it's the same problem exactly, right? There's no difference. That's how we approach them. Okay. As I said, we're going to do more power. We've handled. Okay. So the next one I'm going to be doing after this, we're going to be doing I'm going to do another example, or rather I'll do that as an extra, and we'll move on to the Doppler effect, which is the next one. Some syllabuses do this, some don't. Okay. We're trying to cater here for as many and as wide as possible by putting in sections that people can use and hopefully get the value. Cheers. Thanks for watching. That's the end of the energy section. Ciao.